The opening years of the 20th century presented a profound enigma in physics. J.J. Thomson's plum pudding model, depicting a diffuse positive charge with embedded electrons, failed to account for the results emerging from Geiger and Marsden's experiments. These experiments, employing alpha particles emitted from radium emanation directed at thin gold foils, revealed a startling anomaly: a small, yet significant, number of alpha particles scattered at extremely large angles. This phenomenon directly contradicted the plum pudding model's prediction of only minor deflections. This discrepancy formed the crux of the scientific crisis. Rutherford's 1911 paper address, Rutherford's publication, The Scattering of Alpha and Beta Particles by Matter and the Structure of the Atom, offered a revolutionary solution. He posited a radical departure from the prevailing atomic model. Instead of a diffuse positive charge, Rutherford proposed a novel structure: a single, massive, positively charged nucleus residing at the atom's center. This nucleus, he hypothesized, contained the vast majority of the atom's mass. The electrons, in contrast, occupied a comparatively vast volume surrounding this dense core, accounting for the atom's overall. The theoretical underpinning of Rutherford's hypothesis resided in his derivation of the scattering formula. This formula quantitatively predicted the probability of alpha particle scattering at various angles. The formula, d sigma omega kz1 z2 e24 ek2 csc4 theta2, where d sigma omega represents the differential scattering cross-section, k is Coulomb's constant, z1 and z2 represent the atomic numbers of the alpha particle and target nucleus respectively, E is the elementary charge, Ek is the kinetic energy of the incident alpha particle, and theta is the scattering angle, revealed an inverse fourth power dependence on the sine of half the scattering angle. This precise mathematical prediction beautifully mirrored the experimental observations, providing a strong quantitative basis for the nucleum. The experimental setup itself was crucial. Radium emanation served as the alpha particle source, providing a stream of positively charged particles. These particles impinged on exceedingly thin metal foils, gold being a prime example. The scattered particles were then detected using a scintillating zinc sulfide screen, allowing the precise measurement of scattering angles. The remarkably small number of large angle deflections demonstrated, via the quantitative agreement with the scattering formula, the existence of a compact, highly charged central region within the atom. From the observed scattering data, Rutherford elegantly estimated an upper limit for the nuclear radius. For gold, this upper limit approximated 3.4 x 10 meters. This value represented an astonishingly small fraction of the atom's overall size, solidifying the concept of a minute, dense nucleus. The direct application of Rutherford's work was immediate: the establishment of the nuclear model of the atom, replacing the plum pudding model. This transition not only provided a more precise and accurate atomic model, but also redefined our fundamental understanding of matter. The specific experimental results, particularly the rare yet substantial large angle scattering, directly pointed toward a concentrated positive charge. This directly challenged Thomson's model, whose diffuse charge distribution could not account for such significant deflections. The quantitative agreement between the derived formula and observed experimental data provided the irrefutable mathematical confirmation of this novel atomic picture. Rutherford's work effectively dismantled Thomson's model, offering a replacement that accurately described the experimental results. The precise mathematical formulation of the scattering process, coupled with the experimental verification, solidified the nuclear model's position as a cornerstone of modern physics. Its impact was immediate and profound, revolutionizing our basic understanding of atomic structure. While Rutherford's nuclear atom provided a brilliant solution to the puzzle of alpha particle scattering, it simultaneously created a theoretical crisis of monumental proportions. The model's very elegance concealed a catastrophic instability when viewed through the lens of established 19th century physics. According to the revered laws of Maxwellian electrodynamics, an accelerating charged particle must continuously radiate energy. An electron orbiting a nucleus is in a perpetual state of acceleration. Consequently, classical theory predicted that the atomic electron should lose energy in a fraction of a second, spiraling inexorably inward to collide with a nucleus. The atom, as Rutherford envisioned it, should collapse in a matter of picoseconds, a conclusion completely at odds with the stable existence of matter. This instability paradox was the profound and immediate intellectual challenge that Rutherford's paper bequeathed to the world of theoretical physics. His triumph in experimental physics had created an impasse for theory. The gauntlet was thrown down, and it was a young Danish physicist, Niels Bohr, who picked it up. Having worked in Rutherford's Manchester laboratory, Bohr was intimately familiar with the empirical certainty of the nuclear model. He accepted the central nucleus as a physical reality. His genius lay in recognizing that the solution to the stability, paradox required a radical departure from classical mechanics. In his seminal 1913 trilogy of papers, titled On the Constitution of Atoms and Molecules, Bohr directly addressed the crisis. He courageously postulated that electrons could exist in stable, quantized orbits without radiating energy, a direct contradiction of Maxwell's laws. He further proposed that radiation occurred only when an electron made a quantum leap from one discrete energy level to another. Bohr's model was a hybrid creation, grafting nascent quantum ideas from Planck and Einstein onto Rutherford's classical scale nucleus. It was a bold, and in some ways aesthetically jarring, synthesis, yet it succeeded in explaining the hydrogen spectrum with stunning accuracy. The intellectual lineage is unambiguous. Rutherford's 1911 paper provided the essential architectural problem, and Bohr's 1913 papers offered the first revolutionary blueprint for its quantum solution. The discovery of the nucleus opened an entirely new domain of scientific inquiry. Rutherford himself continued to probe this minuscule, dense region he had revealed. In 1917, through a series of experiments bombarding nitrogen gas with alpha particles, he observed the emission of hydrogen nuclei. He correctly inferred that these particles, which he would later name protons, were fundamental constituents of the nitrogen nucleus. He had, in effect, performed the first artificial nuclear transmutation and identified the first building block of a nucleus. The 1911 paper had established the existence of the nucleus. The 1917 work began to define its composition. The picture remained incomplete, however, as atomic masses were consistently higher than their corresponding atomic numbers suggested. This puzzle was solved in 1932 by Rutherford's student, James Chadwick. Through his own meticulous experiments, Chadwick confirmed the existence of a neutral particle within the nucleus possessing a mass nearly identical to the proton. This particle, the neutron, resolved the mass discrepancy and completed the fundamental picture of the atomic nucleus. The path from the 1911 scattering experiments to the proton and neutron illustrates how one foundational discovery can become the wellspring for an entire field, in this case, the very birth of nuclear physics. Even beyond its role in catalyzing quantum theory and founding nuclear physics, the core principles of the 1911 paper retain a striking modern utility. The physics of particle scattering from a central potential is the direct foundation for a powerful materials science technique known as Rutherford backscattering spectrometry, or RBS. In this application, a beam of light ions, typically helium, is directed at a sample material. By measuring the energy and angle of the backscattered ions, scientists can precisely determine the composition and thickness of thin films, identify elemental profiles as a function of depth, and analyze crystalline structures. The same mathematical relationship between impact parameter, scattering angle, and nuclear charge that Rutherford derived to conceptualize the atom is now a routine analytical tool in semiconductor manufacturing and materials research. This demonstrates an extraordinary longevity of thought, where a century-old discovery continues to provide practical, quantitative insights into the structure of. In conclusion, Rutherford's 1911 paper on the scattering of alpha particles accomplished something far greater than merely replacing one atomic model with another. It acted as a fulcrum upon which the whole of physics pivoted. By providing irrefutable evidence for a dense, charged nucleus, it shattered the framework of classical physics at the atomic scale, rendering the subsequent quantum revolution an absolute necessity. The work established the fundamental architecture of the atom, an architecture that Niels Bohr would soon imbue with quantum rules. It laid the groundwork for Rutherford's own discovery of the proton and for Chadwick's identification of the neutron, thereby inaugurating the field of nuclear physics. Its principles persist today as a vital analytical method in materials science. Rutherford's paper was a moment of profound disruption and creation, a singular achievement that resolved a key experimental anomaly while simultaneously exposing a deep theoretical paradox. This act of discovery and provocation redefined the atom and, in doing so, drafted the initial blueprints for the modern physical world.